Okay, welcome. At one of the keynotes this morning, we heard about how crossovers between different fields of work can produce some interesting results. And our next speaker is very much a proof of that. So please welcome Tornhill.
Thanks a lot, and good afternoon, everyone, and welcome to this session where we'll learn to guide refactorings with something I call a behavioral code analysis. But before we get to that, let's just take a few moments and reflect upon the human potential. Because this is something I started to think about just a while ago. All those amazing, wonderful things humanity has achieved. I mean, already thousands of years ago, we managed to erect the pyramids, and they still stand. Isn't that great? And in more recent time, we have performed amazing scientific breakthroughs. We have managed to sequence the human genome. We have performed grand engineering projects. I mean, we have landed on the moon. And I'm pretty sure that these advances will continue. So in the decades to come, we will see the scientific boundaries expand even more. And we might be able to see things like maybe we're able to tame fusion power and obtain clean energy. That would be great. Or maybe we would even be able to revive the dinosaurs. How cool wouldn't that be? You know, we could build a theme park or something. So as an engineer, I'm pretty fascinated by these advances. But in my second role as a psychologist, I'm much, much more interested in what the limitations are. What are the boundaries of human knowledge? How far can we push it? And I'm pretty sure that there are some things that we will never, ever be able to grasp. And the best example I know upon that is this: human consciousness, the human brain. I'm pretty sure that we will never be able to figure out how our consciousness really works. However, that doesn't mean we won't try. There's actually active research in that very area right now. But then on the other hand, there are some things, some tasks, where we know upfront that this is just impossible. It's never going to work, so we won't even try it. And the best example I know upon that is this: to modify someone else's code. And I think C++ really just adds another dimension to the challenge. And I'm only just half joking here, because I do think this is a hard problem. And the reason I think it's a hard problem is because working with someone else's code is a constant uphill battle. And it's an uphill battle that's very well captured in something called Lehman's laws of software evolution. Now, I'm a big fan of Lehman's laws. First of all, I like them because there are not any real laws in the formal sense of the word. They're more like a set of accurate observations. They're also not that well known, so I try to do my best to popularize them. So let me present just two of those laws to you here right now and see if they resonate with your experience. So let's look at the first law, the law of continuing change, where Lehman claims that the system has to continuously adapt or evolve, or it will become progressively less useful over time. Do you recognize that? So yeah, I think that's the main reason why we keep adding new stuff, new features to our existing code bases, right? What I want you to note now is that there is some conflict to the second law of software evolution, and that's the law of increasing complexity. Because Lehman claims that as a system evolves, its complexity will increase unless we actively try to reduce it. Now, do you see the tension here, right? On one hand, we have to continuously evolve and adapt our products, but as we do, their complexity will increase, which makes it harder to evolve them and continue to change them. So this is a vicious circle that we need to break. And we need to break it by controlling the complexity of our solutions. So let's look into that. And when I talk about complexity, I want you to note that there are basically like two different categories of complexity. On one hand, we have what we call essential complexity. So that's like properties of the very problem we try to solve, the very reason we write a computer program in the first place. And I'm not going to talk about that today. Instead, I'm going to focus on the other side of complexity, the accidental complexity of our code. And with accidental complexity, I'm simply referring to parts of the solution that are more complex than what the problem calls for. And I found that accidental complexity comes in two different shapes as well. So in one case, we might have complex parts. So, you know, those are the parts of your code base where the implementation is simply much more complicated than it could be or than it should be. And then we have the second kind of accidental complexity, where each part is easy enough to understand in isolation, but where the emerging system behavior is anything but simple. We have complex interdependencies. And I'm pretty sure that this second type of complexity is something we will see much more from in the years to come, thanks to the recent hype and popularity around microservices. So in this session, we're going to cover and address both types of complexity. And we're going to do it by using something called a behavioral code analysis. So what is a behavioral code analysis? Well, in a behavioral code analysis, we emphasize the code. The code is important, but we do put less emphasis on the code and much more emphasis and importance to the behavior that led to the current code. That is, we want to look at the evolution and the patterns of the developers and organizations that create the system. And in order to do that, we obviously need to find some kind of behavioral data source. How can we find a behavioral data source from how we developers work with the code? Well, those of you who know me, or maybe have read one of my books or attended my previous sessions, you know that I'm a big fan of version control data. So I guess we all have our odd hobbies, right? This is mine. And the reason I like version control data is because I find it truly fascinating that historically, we in the software industry have used version control data as more or less an overly complicated backup system, and then occasionally as a collaboration tool. And then almost as a side effect, we have built up this wonderful behavioral data source that contains a lot of interesting social information on exactly where we have worked with the code, how we have worked with it. And that's a data source that we're going to tap into today and mine for interesting information. Now, I'm going to show you how that works in just a minute. But before I do that, I want to point out that what you will see today is that I tend to prefer simple metrics when I do a behavioral code analysis. And the reason for that is because I view metrics as a guide, never ever a replacement for anything. In particular, metrics never replace our expertise. Metrics can only help us focus our expertise where it's likely to be needed the most. So that also means that these metrics are not going to stand on their own. They need someone else. They need you. They need a human in the loop. And what a behavioral code analysis helps us with is to view complexity through the lens of that behavioral data. Now, I hope this doesn't sound like I'm too far up in the clouds here. So let's try to make this specific. Let's look at a real code base. And my first case study here is a code base that I think a lot of you might actually carry around in your pocket right now. I want to look at this. I want to look at Android. More specifically, I want to look at the part of Android known as the Platform Framework Base. And as we see, this is a huge code base, 3 million lines of code, most of it Java. And what's even more interesting is that that code has been written by more than 2,000 unique contributors. Now, if you have seen any of my previous sessions, you know that this is something I call a hotspot analysis. So if you have seen this before, you might get a little bit of repetition, but I find that important because a hotspot analysis is like the foundation of all behavioral code analysis. So it's really important that we understand what we see here. So let me walk you through this. This type of visualization is something I call an enclosure diagram. And you might see those large blue circles, the ones that blink on screen right now. Each one of those represents a folder in the codebase, or directory. So this is a hierarchical visualization that follows the folder structure of your code. It's also, wow, a cliffhanger. What is it? I'm curious as well. What could it be? Let's see. So those are the folders. So this is basically a hierarchical visualization. And it's also interactive, right? So we can zoom in on any level of detail that we're interested in. And once we do that, you will see that each file, each Java module is visualized as a circle. And you will see that the circles have different size. That's because size is used to represent something called code complexity. Now, I'm going to show you in a minute how I measure code complexity. But before I do that, I would like to point out that this is actually the least interesting dimension if we're after a refactoring target. And the reason I say that is because complexity has this really fascinating property, that complexity is only a problem when we need to deal with it. So even if we have some complex, overly complex part of the code over here, if we never need to touch it or work with it, well, it might not be optimal, but we are much likely to have much more pressing issues to attend to somewhere else. So in order to prioritize those complex parts of the code, we need to find out, do we actually work with that part of the code or not? And this is data that we can pull out of our version control system. We can look at the change frequency of each module. And we're going to visualize that using color. Now, if you reason about concepts like technical depth, I have found that change frequency is what helps us to calculate an interest rate on any technical depth we might have. So I tend to use change frequency as a proxy for interest rate on technical depth. And when we combine these two dimensions, we're able to identify complicated code that we have to work with often. And those are our hotspots. Now, we're going to return to Android and look at this specific hotspot very soon. But before we do that, I would like to explain how I tend to measure code complexity. Now, you might have heard about metrics like McCabe's cyclomatic complexity, cognitive complexity, nesting complexity, and so on. And what all of those have in common is they tend to focus on this. They tend to focus on different branches and control structures in the code, stuff that adds a cognitive load to the human who's reading the code. Now, the drawback with those kind of metrics is that you need to have language-specific tooling because your tools need to understand the syntax and the semantics of the code. And I find that a bit too constraining because many systems today are polyglot code bases, right? We have multiple different implementation technologies. So ideally, we would like to use one complexity measure no matter what programming language that happens to be in that part of the code. And there's actually one way of doing that. And it's a technique we can learn about by studying visual artists and learn about the concept of negative space, the power of what's absent. So I will claim there's a much simpler view of code complexity here. That's right. The only thing I do is I count the number of indentations in the source code. And now, I know, some of you probably at this moment think, what an absolutely crazy idea. I mean, there are so many good talks at this conference, so many good talks in parallel, and I go and I listen to this guy who claims you can estimate complexity by counting indentations. Well, let me tell you that this is actually a technique that's pretty well studied in empirical research. And it turns out that the number of indentations in your source code has a very strong correlation to the actual complexity, the control structures. And it also has a number of interesting properties. First of all, it's language neutral. So if you work in anything except assembly, this will work really, really well. It's also fast, right? Because you don't need to parse the source code and stuff like that. You can just count the number of indentations. It's really quick, which makes it very well suited for things like trends. And that's what we're going to look into right now. So let's return to Android. So the number one hotspot in Android so far is something called Activity Manager Service. Wow, let's listen to that name once again. Activity Manager Service. Isn't it wonderful? What do we have there? Let's deconstruct it, right? So on one hand, we have something called an activity. It sounds like it could be a concept from a problem domain. Yeah, most likely it is. But then we have two words, manager and service, that each one in isolation hints at a unit with low cohesion. Now, combine that with the fact that we have 20,000 lines of code in that module, and we might just start to suspect that maybe we have a few responsibility too much. Maybe. Well, let's see. So, based on what I've shown you so far, we have some complex code, and there's a very high change frequency of it. Already there, I would suspect that this is a likely refactoring target. It's code that's likely to benefit from improvements because we work with it so much. But the next thing we want to find out is, maybe the organization that works with that code already know about it. So maybe they have started to do improvements to that code. To answer that question, we can use a technique called complexity trends. And this is where we get back to counting indentations. So what I do here is basically I just go to the version control system and then I pull out each historic revision of that code and I count the number of indentations as a proxy for complexity and plot that using the red line here. And then for reference, I plot the blue line, which shows the accumulation of lines of code. So for these hotspots, we do see that this seems to be a growing problem. And it's a growing problem because we see an accumulation in lines of code. And that's always a sign of problem. But what worries me even more is that the complexity seems to increase at an even steeper rate. So what this indicates, taken together, is that most likely the way this hotspot evolves is by additions of deeply nested logic. And that's like kind of the worst complexity you can ever find. It puts a terrible cognitive load on us. So I will claim that this is a pretty good and pretty likely refactoring target. So let's look deeper at this. And the reason I keep using these metrics, like measuring change frequency, is because we're always going to have these trade-offs. And it's always going to be a trade-off versus doing improvements to existing code versus adding new features. Remember the law of continuing change, right? So it's always going to be a trade-off, and this is why I think it's so important to base those decisions on data from how we actually work. And this is where hotspots can help us. But even if we agree that the Activity Manager service, it should indeed be refactored, we cannot really just start to change the code. And I'm going to show you the reason why we cannot really do that. Because remember, there were like 2,000 contributors to Android. So at any given moment, there are likely to be a lot of people working on that code base. So before I attempt any large-scale refactorings, the first thing I do is I go to the version control data and I start to pull out social information. And I plot that for our Activity Manager hotspots using a technique called fractal figures. So what this shows you is basically each one of those slices shows you the relative contributions of each offer over the past 3 months. So if you sum this up, you see that over the past 3 months, there have been 74 contributors to that hotspot. And this is important for us as programmers that want to refactor something, because what this means is that we cannot really just branch out and work on our refactoring for 2 weeks, because we will never, ever be able to deliver it back. Because in the meantime, our colleagues, the other 73 persons, will have been adding new stuff that is likely to be incompatible with our refactorings. So what we need to do here is that we need to refactor as if social factors mattered. And this is a problem I worked on a lot over the past years. And one pattern that I have seen used successfully over and over again is something that I call the Splinter pattern. So the Splinter pattern, the intent of the Splinter pattern is to provide a structured way to break up hotspots into smaller, manageable pieces that can then be divided among several different developers to work on. And I also have to point out that when doing a Splinter refactoring, we are never after perfection. One could even argue that the Splinter itself doesn't really improve the code. What it does, however, is even more important. It creates a new context. The Splinter is about a transformation. It's about getting the code to a state where real improvements can be done, while at the same time minimizing the risk and conflicts due to parallel work. So let's look at an example from an Activity Manager service. And what you see here is it's really just a thin slice of the whole hotspot. But remember, we kind of suspected a problem with low cohesion here. So the first thing I would do in this case would be to identify the different responsibilities of that code. And if you look at the code, you can pretty soon identify a number of behaviors. For example, you might see things like a stack behavior. You might see that there are things like a translucence behavior, an ownership behavior, and so on. And the next thing I do in a Splinter refactoring is that I pick one of those behaviors, and then I copy-paste it. I literally copy-paste it into a new module and try to put a sensible name on it. And once I've done that, I commit the code. Why do I commit at this stage? Well, so far, the only thing we have done is that we have duplicated some code that isn't even used. So this is a completely risk-free commit. and then I pull the latest changes. And what I do next is that I go back to the original context here, and then I start to rip out the implementation details and replace them with a simple delegation to my new Splinter. And then I commit the code. And the reason I do this step is because what I want to do here is that I want to prevent my local refactorings to kind of ripple to the rest of the system. So I want to use the original context as a facade, something that maintains the original API for all the other clients as long as possible. Now, after I've done that, I might start to extract some of the other behaviors. And once we have done that, we have created an entirely new context, because what we now have is individual parts that can be refactored in isolation, while our colleagues continue to evolve other parts of the solution. And the reason we managed to do this is because with the Splinter objects, we have created a better alignment between the problem and the solution domain. And that kind of alignment is exactly what facilitates parallel work by multiple people. And we're going to see more examples on that later today. So with the Splinter, we should use more natural boundaries for multiple people to work on this. And once I've refactored one of those parts in isolation, what I do next is that I do some cleanup as a final step. So I go back to that simple delegating code in the original context, and then I simply throw it away. I delete the code and let the clients access my new Splinter object directly. And if you do this continuously, you will see that eventually the original hotspot might just disappear. Now, the Splinter refactoring is something that might take months on a large hotspot like Activity Manager Service. So, like all large and long-running processes, we need to have continuous feedback on that. And I've found that complexity trends work really well for that too. So what you see here is an example from a real-world Splinter refactoring of a large hotspot. And the reason I show these trends in this case is because refactoring code, it's really, really hard work. And I found that complexity trends like this can serve as motivating feedback to the developers who actually do the refactoring, so that they can see that their efforts have a real measurable effect. Another reason I do this is because, remember, there's always this trade-off between doing improvements versus adding new stuff. So this might also serve as important feedback to our stakeholders, our non-technical stakeholders. I've found that complexity trends work really, really well to show to non-technical managers. You know, everyone can understand that the downwards trend here is generally a good thing, right? And this is important because it lets non-technical managers peek into our otherwise non-accessible world of code. Now, when I did the Splinter refactoring, I started out by saying, all right, let's take one of those behaviors where we identified, and then we copy-paste it to a Splinter object. But I kind of skipped over, where do I start? How do I select that behavior, not one of the others? And this is a challenge in many of those large hotspots, because you have like 20,000 lines of code, so where do you start? Well, what I do when I come across those large hotspots is the following. I use a technique I call an X-ray. So what I do is basically I parse the code into different methods and functions, and then I look at the git log, where do each commit hit inside that file? And then I sum it up, and that basically gives me hotspots on a method level. And that's what I use to prioritize refactorings. Let's look at an example here. These are the local method level hotspots for Activity Manager Service. And we see that the number one hotspot on a method level is something called handle message. Handle message is a method with almost 500 lines of code. That's quite a lot for a method, isn't it? And we can also see, if we look at the change frequency, we see that the developers have made 97 changes to that code just over the past year. So this is like one change every third day. So if that code is overly complex, it's quite likely that we will get a real payoff if we refactor it. And we're going to look into that and see what we can do about handle message in a minute. But before I go there, I would just like to share a few links with you about the tooling I use, because maybe you would like to try this on your own code. So I have to tell you that this is still a young field. There are not many tooling options available, And when I started out with these analyses, in fact, when I wrote my previous book, Your Code is a Crime Scene, like 5 years ago, there weren't any tools available that could do the kind of analysis I wanted to do. So I had to write my own. So I put together a tool suite called CodeMat. It's available on my GitHub page. It's open sourced, and I still do the occasional maintenance of it. What I work on now is something called CodeScene, which is a service that's completely free for open source projects. So if you work in that space or you want to support CodeScene, please have a look at it. What I also want to point out is that I find it truly fascinating that you can get really, really far with a true low-tech approach. I use GitLog for some of these analyses. And I find it fascinating, just to give an example, with GitLog, if you provide a -l flag, then GitLog lets you specify the name of a function in a file, and Git will automatically trace that function's evolution. So this is like a simple, low-tech X-ray technique, right? All right. With the tooling covered, and you're going to get all these slides afterwards, you can check out the links. With the tooling covered, I want us to talk a little bit about code application and dry violations. Don't repeat yourself. So let me start by asking you, how many of you here have ever used a copy-paste detection tool on your code base? Wow, a lot of you, like 1/3, almost half of you. That's a lot. That's a much higher response rate than I normally get. And I find this fascinating because copy-paste detection it's a really old idea. It was pioneered in software in 1992 by Brenda Baker. And yet, it still seems like it hasn't really become mainstream, even though a lot of people here seem to do it. And I think the reason copy-paste detection never became mainstream is because I do think the results from copy-paste detection run are way too depressing. In fact, if you look at the research, you will see that somewhere between 5 to 20% in any code base are duplicated to some extent. That's quite a lot. Even if we pick the lowest number there, let's say we have 3 million lines of Android code. That's a lot of duplicated code. So it becomes hard to act upon that information. And we can pretty much see that if we return to our Android hotspot. Remember the local hotspot we found with the X-ray technique here, handle message. If we look at this code, you can pretty much see that there are large chunks of duplicated code here. And again, this is really just a small slice of the overall hotspot. So now imagine 500 lines of code like that. It's going to be really hard to work with. So the first thing I do once I come across code like this is that I try to identify the commonalities and extract them into a method, and then I parameterize them with the concept that varies. So in this case, and I will actually claim that this is a dry violation because it's exactly the same rule that's applied over and over again. So I would extract that common behavior, and I would put it in a method called execute, and then I would just parameterize it with the method reference, the only thing that varies. And the reason I start here is because once you start to reduce redundant code, what tends to happen is that we tend to reveal the overall algorithm. And that revelation, in turn, informs the next refactoring steps that we take. So in this case, after doing this refactoring, let me show you. So after doing this refactoring, where I extracted the execute method and start to parameterize it, once I've done that, I figured out that, hey, this starts to look a little bit like the design pattern command. So maybe that would be a good next refactoring step. So what I would do next is that I would take each one of those messages that we're supposed to handle, and I would take the logic associated with them, and I would encapsulate that in an object of their own. And if we do that, eventually our whole hotspot method will just disappear. There will be no more handle message, and the word will be in a slightly better place. Because we now have one maintenance problem less, and as a nice side effect, we also get our design to better align with the open-closed principle. Now, I do think that when I start to talk about copy-paste and copy-paste detection, I think it's only fair to also let you in on the dirty secret of copy-paste. And the reason I want to talk about this is because I have found that we developers, we tend to be conditioned to despise copy-paste code. We have learned that it's a bad thing to do. But I will claim that copy-paste in itself is never, ever a problem. Let's say, for example, we have some code over here, we copy-paste it over here, and now those two copies evolve in different directions. One could argue that copy-paste was a good starting point. Or maybe we have some code here, and we copy-paste it over here, and now we never need to touch those copies again. Is it really a problem? No, it isn't. The problem with copy-paste starts once we have some code here, we duplicate it here, here, and here, and now we have a predictable modification pattern across a cluster of copied code. So what we need to do is to find a way to kind of sort out the good copy-paste from the bad. And there's one technique I've been using for that I would like to introduce to you. It's something I call change coupling. And change coupling is a bit different from the way we developers typically talk about coupling. Because when we normally talk about coupling, what we're typically referring to is like a dependency, right? But change coupling is different, because change coupling is something that happens over time. So it's something we can only study by looking at our version control history. Here's how it works. Let's say we have a piece of code here, and we modify the methods A and B together in the first commit. In the next commit we do, we modify something else. In the third commit, we're back to modifying A and B together again. Now, if this is a trend that continues, there has to be some kind of logical relationship between A and B, because they're changing together over time. And this is something we can use to prioritize copy-pasted code to Refactor. And I want to show you an example by showing you one of my favorite code bases, the Linux kernel. And the Linux kernel, I'm so fascinated by this code base because it's truly large scale. You see, it's around 16 million lines of code, so it's really, really big, right? But the number that impresses me here is this one, 15,000 unique contributors. So the fact that they managed to hold that code base together, given that number of people, it's mind-blowing. It's incredibly impressive. So this is a successful social design at scale. Now, if we look at the top hotspot in Linux, when I did this analysis, it's a module called the Intel display. Is anyone familiar with that code? None of you. Cool, I got something new for you. We're going to look a little bit at it. So the Intel display, it's part of the graphics driver for Intel graphics cards. And we see that, again, it's a pretty big file, 11,000 lines of code. It's at least a factor of 20 what I would be comfortable with. So what I do next is, again, I see, all right, is it code that we might have started to reduce in size, or is it code that just keeps accumulating complexity? And it turns out, indeed, it just keeps growing. So if I'm looking to do a strategic refactoring here, what I do first is that I look for duplication, for a repetitive code that I can reduce. So I run a change coupling analysis on the Intel display, and here's what I found. I found that there were two functions. Both of them were named something like finish page flip. And each time you do a change to one of them, you have a predictable change to the other one in 100% of all the cases. And you see a likely explanation for that, because what I do next is I combine that with a copy-paste detection algorithm, and you see that they have 99% similarity. What does that mean? What is 99% similarity? Well, let's look at the code. So what I'm going to do now is that I'm going to put up those two copies next to each other, and your task is to see if you can find some kind of subtle duplication here. Are you ready? You do look ready. So let's look at some C code. Do you see some subtle duplication? That's right. There's a single character difference. That's the only thing that differs. And I have to tell you that this is actually, it's pretty good to find something like that, right? But because it's a low-hanging fruit, I'm not that worried about it. It's pretty simple to refactor, to encapsulate the commonalities, start to parameterize with a small thing that varies. It's easy. I'm much more worried about code like this. The second pair we have here. So we have two functions here. Both are called something like find best DPIL. And again, they change together in 100% of the cases, but their code similarity is only 95%. Interesting. Let's look at the code. What you see here is a perfect example on the most expensive code you can ever have. This code is going to cost a fortune to maintain. And the reason I claim that is because every single developer who looks at this code have to ask the same question. Is this condition that's present in the left-hand side but absent in the right-hand side, is it a bug fix that we forgot to add to the other clone? Or is it a context-specific check, something that can only occur in that calling context? Without more information, we just cannot answer that question. So this is the kind of code where it really pays off to extract the similarities, extract the commonalities, and parameterize them, and let context-specific stuff remain in the calling context. Now, what I want to show you here is that I found that combining copy-paste detection techniques with change coupling measures help us to not only identify but also prioritize the copy-pasted code that really needs our attention. And I have a number of tools here that I typically use to do this stuff. What I want to do next is that I want to point out that code application actually goes way beyond code similarity, like we saw on the previous slides. And this time I want to study a different code base. I want to look at this one, Entity Framework Core. So I know this is mainly a Java conference, but do we happen to have any C# developer in here? 1, 2, 3, 4, cool. Great. So you might be familiar with this one, Entity Framework. It's an object relational mapper from Microsoft. So it's something you use to interact with databases. And when I did a change coupling analysis of that code base, I found something interesting. I found 2 unit tests that always change together. So let's look a little bit at this. Both of them have very similar names. One is called string, starts with method call. The other one is called string, ends with method call. And remember, this is an object relational mapper, right? So what they do here is basically they set up some kind of condition, run something, and look at the generated SQL, and then they compare it against the expected SQL that they have hand-coded here. If you look at that expected SQL, you will see that there's a lot of application. It's obvious, right? The whole first part is identical. So kind of like the gut reflex is to refactor this stuff. Extract the similarities, maybe we could put a nice name on a method somewhere, or since it's just strings, we could even get away with just introducing a symbol, a constant string, right? However, would that make our code better? It would reduce that application, but would it make our code better? No. It would actually make it worse. By reducing that similarity here, what we would do is that we would compress the meaning of our unit tests so that they become hard to understand in isolation. But at the same time, we have some obvious applications. So how can we kind of resolve this conflict? Because we do want to communicate this. Well, we can learn about the technique by taking a detour into a field of psychology called Gestalt. So the Gestalt movement of psychology was something that started in Germany in the 1920s. And the Gestalt psychologists, they set out to formulate a set of principles around how we humans perceive the world. And one of those principles was called the principle of proximity. Now, the proximity principle claims that objects or shapes that are close to another appear to form groups. And I can demonstrate this to you pretty easily. Just have a look at the following picture. How many different groups do you see here? 4? Most people tend to answer 4. But you could equally well answer 2 or 1 or 0, right? Because the only thing that makes us perceive these circles as being in distinct groups is the spacing between them, right? And once you know about the proximity principle, you can see it everywhere. Because it turns out, you know, those marketing people and designers, they really love proximity. So a lot of famous company logos are based on the proximity principle. And I'm pretty sure that the proximity principle is something we can use when we structure code. So let me give you an example. Have a look at the following 2 versions. It's the same program, just structured in 2 different ways. In case A, we want to do a change to this program, and we have to modify 3 adjacent methods. In case B, we also have to modify 3 methods, but now they are distributed across the code base. So I will claim that change A is simpler, easier, and cheaper to do than case B, even if it involves the same amount of code. So proximity is something I often use as a refactoring technique. So let's return to the case study from Entity Framework here, and let's add some more context. When we do that, we see that there are two copy-pasted test cases here. In the full context, they actually have 3 other unit tests interspersed between them. So what I would do in this case is that I would take one of those unit tests and just put it next to the other one. I would just move it inside the source code file. I would refactor for proximity. Because with proximity, we have our code reflecting the changes we do to it. And that serves as a powerful reminder to both the programmer and, more important, the code reader coming after us. Now, the last thing I want to talk about today is this other kind of complexity, where we have complex interdependencies. And the concept of change coupling that I showed you, so far we've only used it on a method and function level. But change coupling, like all behavioral code analysis, can be applied at any level of abstraction. So we can start to identify change coupling between different files. And when we do that, if you do that on your code base, you will see that you get a lot of data. And the reason you get a lot of data is because change coupling in itself, it's neither good nor bad, it's just there. And it turns out a lot of the change coupling is expected. So you might have things like a unit test that changes together with the code under test. That's expected, right? Or maybe an interface that changes together with its implementation. So again, we need to find a way to identify the interesting cases. And there's a tool I use for that, a mental tool. It's something I call the heuristic of surprise. So what I do here is that I look at the change coupling results, and I look at any couples that kind of violates my architectural expectations. Anything that involves a surprise to me. And the reason I use for surprise for that is because surprise is one of the most expensive things you can put into a software architecture. So let's look at an example. Let's look at a code base that I always use as an example on a very well-written and well-designed code base, jUnit 5. How many of you use jUnit 5? So it's a clear majority, cool. So this is code that you rely on. Well, I can relieve you and tell you that if you pick up any one of those hotspots and you look at the code, you will see the code looks really, really good. It's very hard to come up with some kind of suggested improvement to this code because it's already so good. So I kind of tried to set a challenge here and say, all right, but can we find some kind of design problem that isn't visible in the code itself by using change coupling? So I ran a change coupling analysis on a file level. And this is what I found. I found a cluster of unit tests, 8-9 unit tests, that tend to change together in 70% of all commits you do to any one of them. Right? So what this means is typically you have to change a unit test, and you have a predictable change in 8-9 other unit test suites. This looks pretty expensive. So to get more details, I followed up with an X-ray analysis and looked at, all right, but what methods, what unit tests actually change together inside those different files? And this might look a little bit messy, and that's because the original visualization is interactive. So I'm going to walk you through it. Basically, each one of those slices that you see here represents a unit test inside a specific test suite. And if you hover over it, you can see all the other unit tests that are expected to change together with that one. So it's still a lot of data, but at least we're now at the level where we can look at the code. So let's do that. This is an example on what some of those unit tests look like. So if we look at this, we see that there's indeed some kind of repetitive pattern which kind of hints at an abstraction that's really just begging to come out. So let's see where that takes us. What I typically look for in cases like this when it comes to unit tests is that I look for multiple assert statements after each other, because it's almost always a sign that we miss an abstraction. So what I do is I take those multiple assertions and I extract them. I try to put a name on them in a custom assertion method. And I could even use something like the builder pattern to kind of suggest a fluent API that might read well. But the builder pattern isn't important here. The important thing here is that with sensible default behavior and custom assertions, we can get rid of a lot of code this way and minimize the change coupling in the process, which means our code will be easier to maintain because more changes will be local. But even that is not the main point, because I think the big win here is that we get to express our tests and communicate in the language of our domain. And I found that generic assertions are at odds with that goal. So I came to view unit test frameworks as basic building blocks rather than something that you would expose on an application level. All right, I have one more thing that I want to show you. I want to show you how the kind of costs of implicit coupling changes with architectural distance. And that's only because the amount of surprise to the maintenance programmer changes with architectural distance too. And so far, I have ripped through a number of open source projects, right? So I think it's only fair at this point that I start to criticize my own code. So let's have a look at some code I wrote. So this is a piece of code I worked on last year. It's a part of CodeScene. And what I found here was a bit fascinating. I found a piece of closure code over here, which is kind of part of the analysis pipeline. I'm going to talk a little bit more about that tended to change together with a JavaScript file here in the UI. So my first observation here is that this kind of points out that change coupling is a language-neutral concept because it's measured from version control data. It doesn't matter what kind of program language that we use. So you can actually identify implicit dependencies between code written in different languages. However, the reason this popped out to me was because it was surprising. And it was surprising because I happened to know that the code looked a little bit like this. So the closure part was located in one repository, and there was some architectural distance to the UI code. There was no direct dependency between them. So this kind of surprised me. But before I show you what surprise I found, maybe you would like to know, how can we track changes and coupling across code in multiple repositories, different Git repositories? It has to be distinct commits, and that's true. But what's also true is that many organizations tend to include some kind of ticket ID or task reference into the commit messages. And if you do that, you can use that number to kind of relate distinct commits in different repositories to each other. And this is something I use all the time when I investigate microservice systems. So you can actually highlight the logical changes in a microservice system. Now, let's return to the surprise I found here. The next thing I did was, again, I looked at what methods inside those different units change together. And what I found here was interesting. What actually happened was that the closure code, what it did was that it read out a bunch of stuff from Git, calculated some metrics, and populated a result structure. And it turned out that each time I added something to that result structure, I had a predictable change in the UI code in order to present it to the user. So yeah, I know, it might not be a prize-winning design. And I realized that as well, right? So I started to think about this. What can we do instead? Well, we could do stuff like composite UIs, would kind of solve the problem. But I do think that the true root cause of the problem goes much, much deeper. Because what we have here is a classic producer-consumer relationship, right? And the separation into different repositories like backend and UI is accidental. It's only based on technical boundaries. It's based on technical boundaries because I happen to know that one of those modules is JavaScript that's expected to run in a browser, and the other one is closure code I want to run on a server on the backend. But logically, they're part of the same component. They're part of the same concept. So why keep them distinct? So I would actually suggest that we take the JavaScript code and move it next to the closure code, because they do belong together. And that way, we minimize and break those expensive change patterns. So let me leave you with a thought here. Because I do think that with the ever-growing complexity of our software systems, we need to kind of rethink software architecture in the years to come. And I do think that if there's a common theme in this presentation, it is that I think that we need to let features drive architectural building blocks, not technology. And I do think that the behavioral code analysis has a place here, because a behavioral code analysis will give you insights that you cannot get from the code alone. And as such, those kind of analyses, they are here to kind of guide your expertise and attention to the parts of your system that are likely to need it the most, so that you can refactor guided by data. And now, I want to leave you with a number of links in case you want to read more. If you found this interesting, I have a new book about it called Software Design X-Rays that came out earlier this year. And I regularly blog at mpere.com. Now, I'm going to hang around afterwards, and I'd be happy to discuss with you and answer any questions you might have. For now, I really just want to say thanks a lot for showing up today, and may the code be with you. Thanks.